Okay, in today's lecture, we are going to derive the equation for the uniform plane wave. So here are the steps in deriving the equation for uniform plane wave. First, you need to choose the so-called appropriate differential equation, which is appropriate for your propagation environment, including if it's a plane wave or in general, the Cartesian coordinate system is more appropriate. And if the radiation source can be approximated as a point, then spherical coordinate system may be good for the describing the wave behavior in this environment. And also, if the source is a very long line source, then the cylindrical coordinates will be should be considered. So, according to the problem geometry, you should choose the appropriate differential equation. Next, you will need to know the general solution for those differential equations, because the wave equation, as we can see, will be in the form of second-order differential equation, 二次偏微分方程式. And for second-order differential equation, there are general solutions for different coordinate systems. For example, in Cartesian coordinate system, the general solution can be either sinusoidal equation and hypersinusoidal equation, including hypercosine and hypersine. And well, in the following slide, we will explain the difference between sinusoidal and hypersinusoidal equation. And in the cylindrical coordinate system, the general solution can be expressed in terms of Bessel functions. So I guess you have heard the term Bessel functions in your engineering mathematics in your freshman year, but I bet most of you do not understand or do not know the application of Bessel function, and that will be something we'll get in touch with in this subject. And the general solution should be in the form of two traveling waves. That's the reason why hypercosine and hypercosine function are or exponential function are good for describing traveling waves. And the fourth step is to substitute the source condition as well as the boundary condition so that you can get the so-called specific solution. So beginning from the general solution of the partial differential equation, and by applying the source condition and boundary conditions, you may be able to derive the so-called specific solution for your problem. So today we will try to demonstrate these steps. So first is to choose an appropriate differential equation, and the choice is depending on your problem descriptions. For this example, assuming that we have current source flowing in the x direction, and the current source only appear at z equals to 0 position, and the current source is a function of time. So as the time varies, the current will change its magnitude and maybe its directions. So imagine that in this classroom environment, assuming that in the middle of the classroom we have invisible wall made of electrical current. So the electrical current is flowing in the x direction. Okay, so this is the x direction, and this is the y direction, and this is the z direction. So in the middle of our classroom, we have current source. So this coordinate are drawn according to the right-hand screw, okay? So in the middle, which is z equals to 0, in this position, and we have an infinitely large current planes flowing up and down in the x direction. But the current plane is tending infinitely in the z equals to 0 position. So you can imagine there's有一个无限大的这个电流墙在我们教室的中间然后这个电流是上下震荡的 ，OK？ 那么这个上下震荡的电流会产生电磁波，而这个电磁波应该往哪边传播？猜一下嘛就往教室的左边跟右边嘛So the wave propagation direction, as you can imagine, shall be in the positive z and negative z direction due to the presence of the current whirls going up and down in the middle of the classroom. All right? And in this slide, we shows the selection of differential equation. Based on the Faraday's law and Ampere's-Kirchhoff law, we know that the curve E equals to the negative of the time derivative of magnetic flux density, and the curve of H equals to the current J plus the time derivative of displacement flux density, del D over del T. And because in the problem described in the previous slide, we only have currents going up and down in the middle of the classroom. So the source involved is Jx. And Jx is related to what? Is related to Hy. So as you can imagine, using the right-hand screw of Ampere's-Kirchhoff law, the magnetic field associated with currents going up and down is in this way and this way. So the magnetic field intensity H, or magnetic flux density B, shall be in the direction of y direction. It shall be in the y direction. So as you can see from this relationship, Jx is associated with magnetic field in the y direction. And as you can see here, it's also associated to the electrical field in the x direction. And because, beginning from this description, from this equation, because Hy is varying as the position shift 也就是说 Hy 的这个磁场，它在不同的 z 会有一点点不一样这就是你怎么样去解读那一个空间微分的那个意思所以这边你看到的是 Hy 上面的变动跟 z 方向的位置差是有关系的也就是说这个第一个式子告诉你 Jx 的存在 x 方向的电流存在会造成 y 方向的磁场，而这个 y 方向的磁场在 z 方向上面是有变化的所以是等号的左边是空间中的变动，空间中的不一致，等号的右边呢是 它其实有看到时间上面的变动，也就是 dx 对时间的微分哈。不过我们先不急着看后面的那一项，我们先看一下蓝色的箭头右上方是什么 ？Well, according to the Faraday's law, if you have time derivative in the hy direction, which means you also have by variation in terms of t, is associated to the variation of ex in the z direction. So according to the equation in the middle of the top, ex, the difference of ex with respect to z is associated to the time derivative of by. So the presence of Jx introduces the difference in space for hy and by as well. And because Jx is the time variant function, as you can see from the previous slide, we write Jx as a function of t. So the associated magnetic field is also a time variant function. And because B and H the time derivative of B and H are non-zero, it will produce spatial variation, spatial inhomogeneous field for the electrical field in space. So according to the second equation, the time derivative of B in the y direction is associated to spatial variation of E in the x direction. And due to the presence of EX variation, we can come back to this equation again because H is a time variant function. E it will be a time variant function as well. So the time derivative of dx is non-zero too. And as long as dx over del dx over t is non-zero, it shall produce spatial variation for h in the y direction. So these two equations will, the relation between the two equations will keep rolling. So time derivative of h produce spatial derivative of in E, and the time derivative of E will produce spatial variation in h. 所以时变因为电流 Jx 是随时间变化的所以它所对应的磁场 Hy 也会随时间变化。那你拿到右上角去看 Hy 也就是 By 只要会随时间变化，它的时间微分不等于0的话，那它也会对应到空间的 Ex 的变动然后因为 Hy 随时间变化，所以你的 Ex 也是会随时间变化。那既然 Ex 对时间的变动不等于0的话，你回到左下角的1号关系式来看，那一个 Ex 的随时间变动又会再衍生后续的 Hy 在空间上的变化所以这两个关系式可以一直滚下去。这也就是为什么 Maxwell 在整理 Maxwell equation 的时候，看到这两个式子，他就说，应该有个东西叫电磁波 （electromagnetic wave）。虽然说在他生前的时候还没有办法用实验的方法验证电磁波的存在，但是从数学的推导上面看起来，电磁波是可以存在的因为毕竟法拉利定律跟安培定律定律都是根据实际的实验所产生的。Alright, so in this problem, because the setup is relatively is simplified, it's kind of a simplified setup, the electrical current source is in the x direction, therefore the associated magnetic field is in the HY direction, and the associated electrical field is in the EX direction. And the electromagnetic wave is propagating toward positive Z direction, and the possible propagation direction, wave propagation direction is in either the positive Z or negative Z direction. And we can simply describe this relationship using equations 3.71a and b. And you can, as I try to demonstrate, that the interaction between the two equations shall provide the source for propagating electromagnetic wave. All right, so here comes the next step. Step 2, we try to find out the general solution, 一般解, the general solution for the two differential equation. The general solution is assumed that, well, from our previous description about the problem setup, we know that there is an infinite electrical current wall in the middle of the classroom. And due to the time-varying behavior of the electrical current, it shall produce propagating electromagnetic wave to the positive Z and negative Z direction. And once you get away from the middle of the classroom, from the Z equal to 0 position, for any other position other than Z equals to 0, you shall feel, or you can observe the presence of electromagnetic wave. And in those positions, do we have electrical current? No, we don't have electrical current Jx in any other places other than Z equal to 0. So Jx is the so-called source, the electromagnetic wave source. It exists only in the middle of the classroom in the Z equals to 0 position. For any other locations, there are no electrical current source for this problem. So the general solution is derived from the condition that there is no electrical source or electrical current source. So we first set up Jx equals to 0. And this is valid for any place other than the position of Z equals to 0. So any position other than Z equal to 0, you have del Hy over del Z equals to the minus of del dx over del t, and del Ex over del Z equals to the minus of del By over del t. So you have this two relationship. And to facilitate our further derivation, we change By and dx as the product of Hy mu sub 0 and Ex epsilon sub 0. Okay, so we will have a more consistent physical parameters which involves only Ex and Hy. All right, and okay, let me write up these two equations on the board. So what is the next step for the two equation? Well, we try to substitute the second equation into the first one, so that we put the spatial derivation, that is, the derivative over the z direction on both sides of equation 1啊。所以我们试着把下面的式子的关系套到上面式子里头，也就是你这边看到的是 hy 对时间的微分，但是你这边看到 hy 对 z 的微分可以被代换成电场 ex 对时间的微分，啊，而上面的话呢，这边有 hy 啊，但是它是对 t 的微分，那这边是 hy， 但是它对 z 的微分，但我们要怎么做？我们把这一个等于我们把下面的关系套到上面去，所以做法是把原本的上面的 equation 在左右各做一次 z 的空间微分，可以吗？So we perform the spatial derivative over the z direction on both sides of equation 1, as you can see here. And the trick is to the right-hand side of the new equation. The order of a derivative can be interchanged. To the right-hand side, you first perform time derivative for hy, then perform the spatial derivative with respect to the z direction for the derivative result. And if you interchange the differentiation order, you will have this thing that is something like this. And you may ask, is that legal to do so? Is that legitimate to do so? Can we do that? Can we interchange the order of differentiation over time and over space? And the answer is yes, most of the time, okay? Because in our daily experience, time and space are separate. Time and space are related. What happens in time and space are independent. So we always say that we live in a physical world with 3-dimensional in space and 1-dimensional in time, and they don't interact. Okay? And what is the exception? Well, if you hop on a rocket that travels at a speed near or close to the light speed, then the relationship between time and space should be considered. So if you live in an environment that the law of general relativity 就是相对论开始要生效，必须要考虑相对论的时候，这个时候时间跟空间的独立性就可能不再成立了，你就必须要同时考量它们，不然的话，你的在我们大部分可以感受到的坐标系统时空关系里头，时间跟空间是独立的，所以时间的微分跟空间的微分是可以交换的。Okay? So under the assumption that time and space are independent, we can change the order of time and spatial derivative. Then, as you can see, here is in the small parentheses is the del hy over del z. Then you can substitute this relationship in here. So it becomes minus mu sub 0 and again you have minus epsilon sub 0 del Ex over So considering this term, and this term, we can rewrite the relationship as a second-order derivative. As what? As a second-order derivative of Ex with respect of Z equals to mu sub 0 times epsilon sub 0 times the second derivative of Ex with respect to T. Okay? So you have this relationship. So what is the interpretation of this equation? This is the so-called second-order differential equation, and it involves second-order spatial derivative of Ex and the second-order second-order time derivative of Ex. So the second-order spatial derivative of Ex is on the left-hand side of the equation, and the right-hand side is the second-order time derivative of Ex. So this is referred to second-order differential equation, and is also known as the wave equation, 波动方程式。所以在偏微分方程式里头，只要你同时看到空间的二次偏微分以及时间的二次偏微分的话，那你就可以说它是一个波动方程式。只是说这个波动的呈现的形式，一个你可以看，你可以，其实也是跟我们现在生活经验有关啦。一种叫做行进波，就是可以传播的波。另外一种叫什么波？相对于行进波的另外一种波叫什么波？驻波。好，那驻波在什么地方可以观察到？其实发声音就是了，声音其实就是驻波所以，比如说，又要再表演了，所以这个又什么？你透过这个容器或这个共振腔 （resonant cavity）， 好，okay. So here the pitch is different, right? Because the size of the cavity is changed. So the resonant frequency of the cavity is changed as well. So you have the general solution for wave equation can be either traveling wave and standing wave. The wave that is resonant within the cavity is referred to as the standing wave. And the wave, the acoustic wave that propagates from me to you, to your ears, is the traveling wave. So what you need to know is that the solution for wave equation can be either traveling wave or standing wave, or sometimes a mix of the two. All right, so next is to discuss the solution for wave equation. As we already seen, the wave equation associated to our projected scenario is this. The second order spatial derivative of Ex equals to mu sub 0 times epsilon sub 0 times the second order derivative of Ex with respect to T. To simplify the derivation of the solution, we can perform a change of variable, which makes our equations look more concise, looks more simplified. So the change of variable is, we define a new variable tau, which equals to Z times the square root of epsilon sub 0 and mu sub 0. Yeah, right. 因为这边里头那个 mu 跟 epsilon 也就是我们之前提到的介链系数跟介磁系数，看起来有点烦，但它很重要啦，等一下我们会看到它的重要性。所以我们把它做一个变数的代换，也就是把原本的变数是 z 换成是 tau， 而 tau 就定义成是 z 乘上mu 跟 epsilon 的乘积的开根号值。其实你不做这个代换，你也一样可以得到一样的结果啦，哈，其实也可以得到一样的结果，只是这个过程式子过程会看起来有点复杂啊，比较繁杂一点啦，哈，但是不代换也可以。而代换之后，我们看起来比较简洁，大家或许比较容易专注在这一个波动方程式的推导上面，哈。So to simplify or to make our derivation more concise, we use the change of variable to simplify the wave equation into this form, which is, as you can see, looks more concise. The second order derivative of Ex with respect to tau, which is also a spatial derivative, minus the second order derivative of Ex with respect to t equals to 0. Then, according to this relationship, as you can see, is in the form of x to the square minus y to the square equal to 0. What is the solution? X minus y times x plus y equals to 0, right? So both conditions shall satisfy the solution of this second order differential equation. So as you can see here, the solution for Ex must satisfy either one of the condition. It can be the spatial derivative of Ex plus the spatial derivative of Ex the spatial derivative of Ex plus the time derivative of Ex equals to 0, or the spatial derivative of Ex minus the time derivative of Ex equals to 0. So you have two possible solutions. One is del Ex over del t equals to plus or minus of del Ex over del t. 好了，好啦，所以在这边你可以看到，满足这一个波动方程式的两种可能，哈，也就是说 ，Ex 对空间的微分等于正或负的 Ex 对时间的微分，这两种都有可能有解，所以我们接下来的话，对这两种的情形做一个讨论。So let's first consider the case that the del Ex over del tau equals to the minus of del Ex over del t. Now, that is the spatial derivative of Ex equals to the minus of the time derivative of Ex. So suppose, so what is the a likely solution for this equation? Well, this is an important part. The likely solution for this equation is any function that contains a variable in the form of t minus tau. So the function is referred to as function f. And the variable in this function should be t minus tau. Why? Because if the derivative if the variable of the function is t minus tau, then if you perform a space time derivative of f, it equals to f prime. That is the first order derivative of the f function. If you perform a spatial derivative of f, it becomes what? You can minus of f prime. Why? Because t is positive in the variable, and tau is minus tau in the variable. So if you perform the derivative with respect to tau, it comes with a minus sign over here. So if you substitute f into this relationship, okay, so to the left is the special derivative of f with respect to tau, so it becomes minus f prime. And which is a function of t minus tau. And the right hand side, f over t, and I have a minus sign over here. It equals to minus times f prime t minus tau. So as you can see from this relationship, because the time derivative of f is positive f prime, and the special derivative of f is minus f prime. So this relation holds. 所以这样的关系，只要你的方程式的变数是 t 减 tau 这样子的形式的话，它就可以满足我们的波动方程式的一个解。所以这个在左边的空间微分跟左边的空间微分跟右边的时间微分之后，这一个等号的关系还是成立的。所以其中的一种形式的解释，你的波动方程式 f 的解是必须要包含 t 减 tau 的变数。那另外一个变数呢 ？What is the other possible solution? Well, that will be a function comes with a variable of t plus tau. So we identify this function as function g. So if you do the spatial and time derivative of g, you get what? Well, it's still function g. And if you get, g prime, all right, sorry. So if you perform the spatial derivative, you get g prime as well. So in the next slide, if we substitute the two relationships for this equation, and assuming that g is a function containing the variable of t plus tau, then once you perform the spatial derivative and time derivative for the function g, it ends up with g prime equals to g prime. So it's trivial. It's still a legitimate solution for this function. So as we can see from the previous two cases, both f function of t minus tau and the g function of t plus tau are potential solution for this second order derivative function, the wave function. Therefore, we can conclude, or we can substitute both functions f and g as potential solution, possible solution for the EX function. So equation 3.77, we write EX, the solution for the field propagating wave, as a function of AF plus BG. So F and G are the two possible solutions. F is in the form of tau minus t minus tau, and G is in the form of t plus tau. They are both both f and g functions satisfy the wave equation relationship. And what is a and b? Well, a and b are just weightings, they are just constants, 所以 a 跟 b 是权重啦，所以它们可以是任何的常数。只要 a 不等于0，但 b 等于0的话，那就表示什么？这一个解完全是 f 方选来组成。假如说 a 等于0 ，b 不等于0的话，也就是说这个解完成是由 g 方选来代表。只要 a 跟 b 都不等于0的话，那就表示什么？这一个波动方程式的解有部分的是 f 方选来组成，有部分是由 g 方选来代表。OK， 所以 a 跟 b 只是一个常数。那我们需要知道的是，在 general solution 里头，你用 a 跟 b 这两个未知数来代表它 OK 的但是我们最终还是希望知道 a 跟 b 是多少那个就是你要求的所谓的特定解 specific solution。而要知道特定解的话，你就必须要知道这一个波动方程式的 initial condition source function 或者是 boundary condition， 你就需要一些额外的条件来帮助你求解 a 跟 b 的这两个常数的值，这两个权重Alright, so keep in mind that here in equation 3.38, we only attempts to write up the general solution for the propagating electrical field, which is EX. The electrical field is vibrating in the X direction, is propagating on either positive or negative Z direction. It varies with time as a wave, propagating wave. And it can be represented with the composition of AF plus BG. Well, you should notice that for the F function, its variable is T minus Z times square root of mu times epsilon. And for the Z function, is T plus Z times square root of mu times epsilon. And you should have a question is, what difference between the two variables? What is the significance? What is the difference in the significance of the two variables? One is t minus tau, and the other is t plus tau. The simple answer is, if the variable is t minus tau, then the solution represents a wave that is propagating in the positive tau direction or positive z direction. And for the g function, because the variable is in the form of t plus tau, then it represents a component of wave that is propagating in the minus tau direction or minus z direction. So the difference between F and G is the propagating direction. Is the propagating direction. And we shall demonstrate this through an example. Before we do that, we already write up the general solution for the for what? For the electrical field. And in this slide, so this is the general solution for the electrical field. And what is the general solution for the magnetic field? So we use this relationship that the general solution for the magnetic field, that is Hy, can be derived by first perform a special derivative of Ex with respect to Z, then perform a time integration, an integration over the time domain so that we can get Hy. So Hy, the special derivative of Ex over Z equals to the minus of mu sub 0 times the time derivative of Hy. So we do the special derivative of Ex, which is AF plus BG. So it becomes AF prime plus BG prime. And note that the first terms comes with a minus sign. Why? Because the variable has a minus sign over here, so it comes with a minus sign. And because the second term, you have a positive z, you have a t plus z, so the derivative of it is still positive. So the second step is perform integration of hy with respect to t. So it becomes this. So notice that the general solution of Ex is F plus BG. But the general solution for Hy is so it looks pretty similar with a tiny difference over here. Now, this is AF plus BG, but the general solution for Hy is AF minus BZ. And it also comes with this part, square root of mu over epsilon. Okay, and you should verify this relationship on this slide. So be sure to do this at home. Well, I guess our time's up for the meantime. So, so let me put it simply. Put it really quickly. F function represents a function that is propagating to the right, propagating in the positive tau direction or positive z direction. So here is an example. If we simply define as f as the square of the variable, that is t minus tau to the square, then at t equals to 0, you found the dip of the parabola function is at z equal to 0. On the other hand, if tau is increased to square root of mu and epsilon, then the minimum of this parabolic function is moved to 1. So as the time progresses, the dip, the minimum of this parabolic function will move further to the right. 所以这边看到的是，当你的那个变数是定义为 t 减 tau 的形式的时候，随着时间的推移，这一个波形会往右边移动。而反过来，假如你把这一个 function 写作是 g function 的话，那它的那个漂移的方向就往左边移动。所以 f 跟 g 的差别是一个往正 z 的方向传播，一个是往负 z 的方向传播。所以它其实代表的是往正向传播的成分跟往负向传播的成分。所以 general solution 对于电场的 general solution 就可以把它理解为是正 z 方向传播的成分加上负 z 方向的传播成分，只是它们的比重我们还不晓得因为目前 AF 加 BG 只是一个 general 的一个解那特定解的话，你还要带入更多的条件。好，我们礼拜四再做讨论了那考卷我改好了，现在是给